First, let me have a revision of whatever we discussed till now under partial order relation. Okay, partial order relation is nothing but a relation which is reflexive, antisymmetric, and transitive. So because of reflexive property, at every vertex we have loop. Because of antisymmetric property, we have only unidirectional edges. Because of transitive property, so if there is an edge from x to y and edge from y to z, then there should be an edge from x to z. And now when we are writing the asset diagram, so we're just keeping the things simple. So what we are doing here, so we are not writing the loops explicitly. Okay, so we are not writing the loops explicitly. Instead, so the convention, so if we just write the dot, we are supposed to read the dot as vertex as well as the loop at that vertex. That's the first point. And we are using only dots to represent the vertices. So we are no more using circles to represent the vertices here. First point. And the second point is we are using the convention of reading the graph from bottom to top. So with this convention, in case of when we are drawing the edges, unidirectional edges, we are drawing those edges in what? Upward direction without mentioning the arrow. And since we are reading the graph from bottom to top, with that convention, so we are going to get an edge A to B. Okay, in this case, we are going to get an edge A to B, and we won't get an edge from B to A because we are reading from bottom to top. We are not reading from in this direction, in the opposite direction. And since R is transitive, we are expecting there should be an edge from between A and C. So when we have edge from A to B and B to C, and we are not mentioning this again, the convention will take care of that. So here I need to read it as A comma A, A comma B, A comma C, then B comma B, B comma C, then C comma C. So even if I have got one more edge here, I should read up to there. So A to A to B, A to C, and A to D, like that. And with this basic idea, so we in the last class we were drawing, we draw asset diagrams. Okay, asset diagram for the posets. Okay, it is not digraph, I'm sorry. This is not the digraph, it should be asset diagram. So digraph represents directed graphs where the edges are edges carry directions. So it is not the thing here. So asset diagram, the posets. And we teach it here, and you people were comfortable with these things. So we discussed more problems to make sure you people are comfortable with the concepts. Then afterwards we define total order relation. What is total order? If we have a poset, and in that poset, that set A is called the partially ordered set, as the relation R defined on set A is partial order relation. So further, if we can show that there is a relation between every pair of elements, so definitely x comma y and y comma x both not present in my relation because R is antisymmetric. We are expecting only x comma y is present or y comma x is present in the relation. So for every xy belongs to A, if any one of this is part of my relation, then we claim it should be true for what? For every pair, for every xy belongs to A, it should be true. So in that case, we call this relation R as total order relation, and the set A is totally ordered set. That is, all the elements of set A are in one particular order. Okay, and topological sorting algorithm. So we learned how to convert a given partial order relation into total order relation. If the given relation is not total order, if the given relation itself is a total order, we do not have anything to do there. Okay, it just remains. Even if we just went through the topological sorting algorithm, you're going to end up with the same total order relation. That's why if the given graph is representing total order relation, in that case, please don't make use of topological sorting algorithm. It is not required. If the question is to topologically sort the total order relation, we are just mentioning that the given relation is a total order given asset diagram represents a total order relation. So we need not to topologically sort it. It's already total order relation. That's all. That is what the conclusion we can make. But in these kind of examples, so we can note that there is no connection between B and C. So this is enough to say this is not a total order relation. So to have the total order relation, so what we did here, So first step is call the given graph as h1 and identify one vertex from the graph which is not the source for any edge. So in this example, E is the only vertex which is not source for any edge. So what I'm supposed to do, I need to call this one as V1. Now we are supposed to delete this vertex. See, delete a vertex is nothing but it is not just about deleting that vertex. Along with that, we are also supposed to delete the edges which are depending on that vertex. Please keep this in mind. Edges always depends on the vertices. So if I delete a vertex, along with that vertex, the edges depending on that vertex also deleted. So that is what we did here. E is deleted. Along with that, that corresponding edge also deleted. So this is what the resulting graph, call that one as H2. Now find the corresponding vertex V2. So repeat the same process. That is, how do we identify V2? Identify a vertex in the Hasse diagram H2. So which is not the source for any edge. That is D. Okay, and you're supposed to delete that vertex along with the edges which are terminating at that vertex. That gives the graph H3. Do the same thing again. Now identify the vertex which is not the source for any edge. Now we have two options, B as well C. So now it is left to us. So it depends on my interest, whether I'm interested in physics books or chemistry books. It doesn't make any difference. So with respect to the order, so it depends on my interest. So I choose B. If that is the case, I need to delete this vertex along with this edge. If I choose C, in that case, I need to delete this vertex along with this edge A to C. Okay. Okay, now what we did here, we deleted B along with this edge. So now the resulting graph is H4. Now do the same thing, and we do not have any other option here, much option. We have got only one option, that is the C. That should be the vertex which is not source for any edge. So identify this vertex, delete the corresponding vertex and the edge, so that we will get the resulting graph is just A. Now repeat the process, just delete this vertex and the process is done, which is my V5. Now the total order relation is given by what? So V5, the vertex which is deleted at the end should be at the bottom level, and the vertex which is deleted in the beginning, that should be at the top. So this less than just represents the order in which we are supposed to place the elements, so in the graph. So it just speaks about that. Okay, so that is what we did here. V5 is at the bottom, V1 is at the top. And I told you people to do this problem. Have you all done this problem? Friends, have you done this problem? Hello? No. Why? What is the reason? Okay, so but still I just want you people to complete that problem. I'm not doing it. So instead I will just take up a different example to handle. So have a look at this question. Just see what this question is demanding us to do. For the following Hasse diagram, write the relation R and the corresponding matrix digraph representation. Also topologically sort them. Okay, let me take up this example. So you will try the second one. I gave this one for homework. I hope you people okay. People told me like you are not done. Okay, it's fine. So do it today. Okay, now let me try this problem, so that through this we can just revise what we did in the last class. Okay, so this is the Hasse diagram for the Hasse diagram of a particular relation. First we need to write the relation R. Okay, before writing the relation R, I need to write the set A. Yes, what is set A in this problem? Friends, what is the set A? You people can hear me, right? Yes, all the vertices we need to write. So I just written now. Okay, next. Okay, we need to write the relation R now. The corresponding relation R is equal. Can you give me the elements of this relation R? Please read this graph. If people know the convention of reading this graph, just give me the elements. Yes. Next. Good. Done. Next. Yes, 4, 4. Good. Okay, I just completed this part. Okay, 2, 2. Then very good. It's 2, 5. 2, 6. That is what we have from 2. Good. Starting with 3. Yeah. Yes. Good. Starting with 5. Yeah. Good. So these are the only elements which are present in our relation R. Okay, so very good. So the convention which we have used. So read this graph is right. This is how we are supposed to read the graph. This is how we construct the assay diagram also. Okay, this is the first part of the problem is done. Next, write the corresponding matrix and digraph representations. Let me complete this. Okay, matrix is required for us. So 1, 2, 3, 4, 5, 6. 6 elements are there here. So definitely it will be what? 6 cross 6 matrix. 1, 2, 3, 4, 5, 6. Okay, 6 rows. 1, 2, 3, 4, 5, 6. 6 columns. Now let me write the elements of the matrix. How do we represent the elements? So by using 0 and 1. If an element is present in the relation, we represent it as 1. If an element is absent in the relation, we represent it as 0. So 1, 1 is present, 1, 4 is present, 1, 6 is present. So these 3 are absent. Next, so starting with 4, only 4, 4 is present, 4, 6 is present. So these elements has to be zeros. Good. Next 6. So only 6, 6 is present. The remaining entries are zeros. Okay. Next starting with 2. So 2, 2, 2, 5, 2, 6. So these entries are zeros. Starting with 3. 3, 3, 3, 5, 3, 6. So these entries has to be zeros. Starting with 5, it's 5, 5 and 5, 6. And you can note that this is representing, this digraph is, or this matrix is representing reflexive property, because every entry along the principal diagonal is 1. Okay, actually in one of the question paper, this is what I saw when they were so this was the question. The question was quite similar to this one. And when I went for the evaluation, so actually it's a final exam evaluation. I think it is in the last academic year. Yeah. So in most of the papers I gave 0 marks for this one, because they missed the loops. So they are written remaining all vertices. So they have missed loops. So 1, 1 is missing. 2, 2, 3, they have missed loops. So they wrote every entry along the principal diagonal 0. Okay, so we can't see them explicitly, but we know that we have loop at every vertex. Please keep this in mind. Assay diagram speaks about the relation which is reflexive, antisymmetric and transitive. So those properties are supposed to be taken care. And in few papers I also saw that. So actually here I am supposed to read 2, 6 also, right? So they have missed 2, 6 because there is no edge from 2 to 6. So then we do not have it explicitly, but we know it is present implicitly because of transitive property. With the convention we are supposed to read 2, 6 also here. Okay. Yeah, and that can be seen. We can also see that it is upper triangular matrix, or it will be lower triangular matrix. Any one will be true with respect to antisymmetrics. If we are talking about antisymmetric relation, so definitely we'll be having upper triangular matrix or lower triangular matrix. Any one will be true. Okay, next let me discuss about what digraph representations. Okay, for digraph you can use dots, otherwise small circles to represent them. So 1, 2, 3, 4, 5, 6. Now let me draw the edges. 1 to 1. Okay, so I will just write the loops later. So 1 to 4 is there. Okay, I'll just keep it to a side. So 1 to 4. Next 1 to 6 is there. Next from 2, it's 2 to 2, 2 to 5. Okay, 2 to 5 is there, and you also have 2 to 6. That's good. Next one 3, 3 to 3 is there, 3 to 5, 3 to 6. So 3 to 5, 3 to 6. And next with 4, 4 to 4, 4 to 6. Next with 5, 5 to 5, 5 to 6. Next from 6, 6 to 6. So we have loop at every vertex. Okay, this is our graph. Okay, this is for 6 marks. See, so simple. It is in almost in 2 to 3 in recent question papers you are finding this kind of questions. Okay, so this is so simple. For the given assay diagram, you written the relation, matrix, and the corresponding diagram. The problem is not yet over. The question continues. You are supposed to topologically sort this. Okay, first let me write the given graph. So what this given graph is. Okay, this is the given graph. So the vertices are 1, that is 4, 6, 5, 2, and 3. So what's the step number 1? We'll call this one as H1. So now identify the vertex V1. So V1 is what? A vertex which is free, which is not a source for any edge. That is a vertex from which no edge begins. So in this example, we can find only one vertex of that kind, that is 6. Okay, V1 is 6. Next, what should be done? Now I need to delete this vertex 6 along with the edges which are terminating at this vertex. So which means our resulting graph is this. So this is my new graph, H2. Now can you tell me what should be my V2? Friends, what should be my V2 now? From this H2, what should be? Very good. We have got two choices, 4 or 5. That's why I told you people that just because of these choices, so the total order whatever we are going to get, that is not unique. It changes from person to person, or changes from how we are going to choose between 4 and 5. Okay, if I just go with V2 is equal to 4, in that case our resulting graph is this. So resulting graph just contains, so this one part along with that the vertex 1. Okay, so this is our V2 and this is our resulting assay diagram H3. Okay, so now what is our V3? For V3 how many choices we have? Yes, 1 and 5 are the two choices. Which one you want to choose now? Okay, I want to go with 1. Okay, let P3 is equal to 1. So therefore my H4 is what? So this is what the graph for our new graph H4. So because this vertex is deleted and the edges which are terminating at this vertex, no edges, so you're just deleting that vertex, that's all. So next one is V4. So for V4, how many choices we have? For V4 we have only one choice, so that is 5 itself. So 5 is the only vertex that we can delete from here. So the resulting graph is we are supposed to delete this vertex 5 and this two edges. So this is vertex 2, this is vertex 3, and we are calling this one as H5. So now we have two choices again. So which one you want to choose? 2 or 3? Okay, if you are choosing 2, our H6 will be just vertex 3. Now I just need to identify this as V6 and delete this vertex from here. So if there is no OC diagram, stop the process and write your total added relation is what? This is V6 less than V5 less than V4 less than V3 less than V2 less than V1. So now I can write the total added relation as well. Okay, one straight line is enough. So one straight line will just take care of this. And so we know our V1 is given by 6. So that should be the vertex which we deleted at the first, that should be at the top. So V6 should be at the bottom. So this is 3, next 2, next one is 5, next one is 1, next vertex is 4, and next vertex is 6. And this is definitely not unique, so you people know the reason. So you can, instead of choosing 2 and 3 here, you can just choose 3 first, then 2 in the second, or between 1 and 4 you can choose 4 first, 1 second, like this. You have got many other choices. So because of that, so this is what the total added relation according to the what I have chosen. Okay, so any doubts in this, friends? Okay, that's fine. So definitely now you people can just handle these problems. So this will x divides y, you people, we have done it. So even this is x divides y subset problem we already discussed, and even we have discussed this problem. Now you people know for the given assay diagram how to write the matrix, digraph, relation, and also how to write how to topologically sort. You people know all this. Okay, so there's one more question they have given here. Okay, please do this problem. So just give a try to this. Friends, make a note of this question and please try it. Please tell me the elements of this set. So what are the elements of R? Okay, at least write the assay diagram. 1 divides 2. Okay, and the question is not to write the relation here. Okay, if you want to write, you write it. Otherwise, directly go for the asset diagram. The question starts with draw the asset diagram. Okay, 1 divides 2. Next, what should be written? What should be written? Yes, 2 divides 4. Yes, 4 divides 8. Okay, next. Okay, 2 divides 4, 4 divides 8. So, does 4 divides any other number? Yes, 4 divides one more number, that is 12. Okay, I'll just keep this to this side. And it is not something mandatory. So, just for a change, I'll just keep it to this side. This is 8 and 4 also divides 12. Let me write that. Okay, so 4 divides only 8 and 12. That's done. Now, if I just come back to 2. So, 2 also divides 6. That is not taken care. So, that can be written right. So, 2 divides 6. We write this. And 6 divides what? 12. Okay, this part is done. So, 2 divides 6. 12. So 2 divides 4, that is written 2 divides 6, 2 divides 8 and 12. So everything is taken care here. Now come back to 1. So 1 divides 3, that is missing. Let me write that. And 3 divides 6. And 3 divides 12. That part is taken care of. So this is what the asset diagram corresponds to. This relation. So A divides B. Now please write the matrix for this. The question is not to write the diagram, only the matrix is enough for this in this problem. So 1, 2, 3, 4, 6, 8, 12. So 1, 2, 3, 4, 6, 8, 12. So starting with 1. So 1 is related to remaining all elements here. Starting with 2. It is related to itself. It is related to 4, it is related to 2, right? 2 is related to 4, 2 is related to 6, 2 is related to 8, 2 is related to 12. So these entries has to be zeros. Starting with 3. So 3 divides itself, 3 divides 6, 3 divides 12. The remaining entries are zeros. Starting with 4. So 4 divides itself, 4 divides 8, 4 divides 12. So these entries has to be zeros. Starting with 6, 6 divides itself, 6 divides 12. The remaining entries has to be zeros. Now starting with 8. So 8 divides 8 is the only entry which is present in it. The remaining entries are zeros. And with 12, so 12 divides itself is the only possible entry. So this is the asset diagram for this. So this is the matrix for this. And please topologically sort this. And the steps are mandatory in the exam. Okay, in the internals, the steps are mandatory. So please don't write. I've seen students doing this. So they will just check like this. Okay, I can take V1 is 12. So this will go. So this is my V2. And then afterwards I can delete this one. Then the next element is V4. So don't choose elements like that. So show step by step. So what is your initial asset diagram? After choosing V1 is equal to 12, what happened? Or if you choose 8, what happens? It should show step by step. So till 1. Delete each vertex one by one. Finally, you just write the total order corresponds to the operation you performed. All of you, please do this. Is it done? Yeah. So can you give me your total order relation after you have got? Okay, first. Okay, no, it should not be V7, it should be V1. Okay, so first element should be V1, that's what I'm telling you. Okay, so V1 is 8. Next, so V2 has to be 12, no option. Next, okay, for V3 we had two options, 4 and 6. You are choosing 4, that's good. V4, 6, okay, that's good. V5, okay, good. Yeah, okay. V6 is 2, V7 is 1, that's good. So this is the total order relation. Your part corresponds to this. Okay, so I hope you people are comfortable with this concept. So we have left with only one more concept, that is extremal elements in POSIX. That's what we are going to discuss at 10 o'clock. And so this completes the relations part. So that's once again very simple. It directly depends on your visualization. Like you are supposed to look into the Hussey diagram and you should need to identify what is maximal, minimal, extremal elements. We need to identify. We'll discuss that in detail. So thank you all.